questions. I'd look. I was a lot further along. Um, so I got behind this semester. So a lot of these questions I'm going to push to exam 2. You know. Yeah, like for example, question number 14 will go to exam 2. And 22, I'm sorry? No. Did you take a look at the practice test I put on Canvas? Okay. The question was about the key for this. So 22, 23, 24 will go on the next test. '30 is okay, but I realize it. Yeah. There's different strategies for multiple choice tests. So for example, number 30, it's an unknown compound that contains carbon, hydrogen, oxygen, so A, B, and D can automatically be eliminated. And so if you have to guess, you might get a 50% chance of guessing C or E. The ratio might be screwed up in C. But the mass works out, you know. So, I haven't finished this quite yet. But 30 is okay, 31's okay, 32's okay. 33, that's going to be exam 2. 34 is okay. 35 is exam 2.
Professor,
yeah.
The sample exam you gave us is different from that one.
Oh, is it?
Yeah.
Oops. What was the sample exam number I gave you guys? Spring 23. Oops. Maybe I have a key for that one already made up. I hope I have a key because I don't want to make a key. I didn't make a key because I mean, it's open book, so you should be able to get the correct answer, you know, with open book. The thing is, once you start working in science, there's no answer key, there's no answer book. I mean, that's normally, otherwise, if there's an answer key or answer book, then you're just doing something that somebody's already done. So you're reinventing the wheel. So how many years of your life are you going to dedicate to reinventing the wheel, which was invented so long ago, you know? And so you're doing new stuff usually. And so what you have to do is you have to figure out ways to check your answer. And so there are different strategies that you use to self-check your answer first, and then you can have others check it as well. And so I have mixed feelings about answer keys for something that is at home. And this goes for, like, you know, open book exam is totally different than like a closed book exam, you know, in terms of the types of questions asked and that type of stuff. All right, thanks for catching that. Otherwise, I would have been wasting a lot more time. So I think, did I already tell you which questions are going to be pushed? It depends on how far I get in the semester. That dictates, you know, this is why it's like if I miss a lot of people miss class, and it doesn't bother them, but when I missed a class, I felt kind of lost, you know. I didn't know what to focus on, and so I never missed class. I always attended every day, except one day. Shoot. The one day I missed, I asked the It was a graduate class. I was an undergraduate at the time, so I asked one of the graduate students, and the graduate student was actually working in the professor's group, so I thought he would know for sure. So I asked him, is the test, the final exam comprehensive, or does it cover just the last half of the course? And he said, oh yeah, it's comprehensive for sure. So, you know, I thought his information was reliable because he works in his laboratory, the professor's laboratory. So, so I studied from the beginning to the end. And do you know the final exam wasn't comprehensive? The final exam just covered the last half of the course. So I wasted so much time studying the first half of the course. So that was my fault. And then, you know, they didn't have things recorded or anything like that. I should have asked the professor. But I thought, well, the grad students good. This is a grad course. There are only 10 students, I think. 10 or 15 students in the class altogether. So if I miss a class, then I feel totally lost because I don't know what to study. Well, you'll probably feel lost here because, like these, I haven't even talked about. You know, which species is most electron rich? So 23, 24, ignore those for this test.
Questions that are like 24.
Yep.
27's okay. The other exam, I delved much deeper into organic nomenclature. That one I just had up, so completely ignored that one, even though it's on the recording. Which species is most electron poor? You could ignore that one too. But we want to just look at the formula because if we know the composition, and the structure, we can determine a lot of its properties, or at least try to predict a lot of its properties. And this is one of the properties we look at. You know, is it flammable? When I say electron poor, that means which of these is the least flammable. You know, electron rich, which one of these is the most flammable? You know, a lot of these organics are quite flammable, but not all of them. Like CO2, can you burn CO2? It's maxed out. You aren't going to be able to burn it. So CO2 is completely maxed out. 29's okay. 30 is okay, except this is a twist on there. 31. There's only one type of molecular motion. Actually, how many types of motion are there? 3 types. Do you know motion? There's translational motion, rotational, and vibrational. Does anybody have a question on any of these specific ones? In water at room temperature, all molecules have the same energy. I don't know if I don't think I talked about this. And so this is the thermal distribution. I don't think I talked about it this semester. Each semester I get off on tangents sometimes, so if I get off on a tangent, then I'm going to test them on it, probably. This one too, Maxwell-Boltzmann, 33 and 34 are the same topic. So 33, 34, don't worry about that. We're going to talk about Maxwell-Boltzmann and thermal distributions in the gas chapter, so let's wait to talk about these in chapter 6. For some reason I was talking about this particular semester I was talking a lot more about potential energy, kinetic energy, energy in general. And so you should, this is why I say you should study from your notes, because then you know, because you know, if I didn't talk about the Maxwell-Boltzmann distribution, I'll probably forget about it when I write the test. You know, probably just remember the stuff I talked about. It's fresh in my memory. 35 for sure. Talked about that a bunch of times. And 36, yes. Then some nomenclature. You can see the nomenclature for the organics is not going to be terrible. Although this might be. I mean, this is how many carbons? 6. And you know what we use? or the parent. Huh?
Is it shared? Does it happen to be shared?
I'm sorry?
Does it happen to be shared?
Happening to be shared?
Sugar.
Oh, sugar? No. Sugars are, they have these guys. Sugars, alcohols, and then you have another group on there that could be in sugar. A lot of sugars are just like more complex alcohol molecules. If you want to see what a sugar looks like, let's take a look at glucose and fructose.
So, does that one have to do with icing or something like,
Does it have to do with what?
isomers?
Isomers? Yeah, but did I talk about isomers?
No.
No. Do you think I'm going to ask you about isomers on this test? Did I have homework problems with isomers?
Yeah.
Yeah. Okay, then I might ask you. I would look at the homework problems. If I ask you about isomers, sometimes I don't have time. The thing about isomers is I probably had homework because when we really discuss isomers is when we get to Lewis structure chapter. And so you guys remember what isomers are. Isomers are different structures for the same composition, same formula. So ethanol, this is why we like structural formulas. Like, if you look at sucrose, you see sucrose is a lot of alcohols on sucrose. There's also these things, which are, we call these ether type bonds. Different forms. So there's different groups there. So sometimes you'll hear the term sugar alcohol. So these are sucrose here. The answer I was looking for is hex. If you have 6, it's hex. And we call this hexane. You know, if there's a double bond or a triple bond, we show it. So this is all single bonds. So normally there'd be a double bond. You've got to get rid of 2 hydrogens, put a double bond in there. Triple bond, you've got to get rid of another 2 hydrogens. Triple bond. So that's hexane. Like with 1 carbon, we call it what? Methane. 2 carbons, ethane, propane. And that's 6 carbons, hexane. What's that? Butane, like butane and butane lighters. It's interesting. Methane, we'll start looking at properties. Methane is a gas, liquid, or solid? Methane, gas. Ethane? Ethane is a gas also. Propane? Propane in the propane tank is a liquid. They put it under pressure, and under the pressure it liquefies. So you can shake the tank, you hear the propane liquid. But when you open the valve, it comes off, it boils off as a gas. And so when it goes to the barbecue or whatever, it's in the gas phase. Whereas butane is under normal conditions, butane is a liquid. Pentane's a liquid, hexane's a liquid. Hexane is a very common organic solvent. Does somebody remember what I talked about hexane in class about? Was it maybe in lab? It was in lab. I briefly mentioned hexane. I talked about dissolving things. Sometimes it's very difficult to dissolve things, and so we try different solvents. Hexane is one of the most common solvents that we use for dissolving nonpolar things like candles. So I talked about dissolving candles with hexane. How about this one? What is this one here?
Ethanol.
Ethanol, good. Ethanol is so common, the alcohol, that you should recognize its formula. Now, ethanol, there's an isomer of ethanol called dimethyl ether. And you definitely don't want to drink dimethyl ether, even though it has the same formula. And so This would be an isomer. Oops. Actually, let's just do it. Yeah. So we know ethanol is CH3CH2OH. Dimethyl ether is CH3OCH3. And they both have the same molecular formula, that is C2H6O. And dimethyl ether is C2H6O. So this is what we mean by isomers. Isomers have the same composition here, 2 carbons, 6 hydrogens, 1 oxygen, but different structures. And if they have different structures, they're going to have different properties. So you don't want to drink this. Dimethyl ether will cause you trouble, but ethanol in small amounts is okay. Isopropyl alcohol, I skipped that. Methanol, all right. All these are all right. Isopropyl alcohol, you can skip this one. I don't want, sometimes I talk a lot more about a specific topic, like organic nomenclature. I'll talk more about this as we go along. But don't bother, you don't have to bother memorizing it. It's rubbing alcohol. .38's okay, except I had a question about fluid ounces. You know, how many ounces in a pound? 16 ounces in a pound. That's just the weight, ounces. But we have the fluid ounces. You know, how many ounces in a cup? Do you know how many ounces are in a cup? Is it a cup? 16? 16 ounces in a pint. Have you heard of that? 16 ounces in a pint. So if you remember 16 ounces in a pint, that's correct. A lot of people will remember that. How many cups in a pint? Well, you know, I had to learn these all, like, in elementary school, memorize all these, but I got a lot of questions. What is a fluid ounce on this exam? So I just gave people how many ounces in a I think I might have given them, I don't know, how many ounces in a cup. Some people know how many ounces in a gallon or half gallon, you know, because it's written on there, 1/2 gallon is 128 ounces or something, fluid ounces. You seen that? So this is a different generation, so maybe you don't need to know this.
Maybe you should go over the kingdom of the gallon.
Oh yeah, right. That's the kingdom of the gallon. Yeah, that's actually pretty good, but I think maybe we'll skip it this time because I'll just give it to you. If you forgot an imperial unit conversion, I'll just give it to you. For sure, like feet. Kingdom of a gallon, you should talk to Ashley here. And she has a great way of remembering these things, you know. And in fact, that's an excellent way to remember a lot of stuff. All right, number 39 is the yes. Number 39, this is a more challenging stoichiometry problem. And so this doesn't deal with percent, whatever, but you should do that. Now, this one is a multiple unknown multiple equation problem. So isomers, I wouldn't worry. I'm going to talk about those. This is just like a little pre-thing, you know, to get you ready when we go into isomers in chapter 9, 8, 9, I think. So don't worry about isomers for this test. A 0.275 gram sample of an aluminum, although nomenclature, you do have to worry. Did you guys memorize the eights? The eights? A lot of the eights we could get off the periodic table, but did you memorize all the eights I told you to memorize? Does somebody have them? You have them, Ashley? Or
Like
borate?
nitrate.
No, nitrate you could get off the periodic table. The ones that you have to memorize would be borate, and then, if you do it in the order I gave you, it was borate, and then
Oh.
silicate, and then
So,
chromate, dichromate, permanganate, acetate, oxalate. You guys memorize those? Nitrate we could get off the periodic table based on the pattern. Carbonate, nitrate, fluorate, chlorate, bromate, iodate, phosphate, sulfate, arsenate, selenate, tellurate, antinomoate. All those we can get off the periodic table.
I would argue that you have to memorize nitrate because it doesn't go with like the pattern of the charges.
Well, why doesn't it go with the pattern of the charges? Because I see it, when I look at this, it does go with the pattern of the charges. This is still continuing this aside over here. Borate is BO3 minus, carbonate is, so the pattern of the charges tells me that nitrate should be NO3 minus. And so we read it left to right. Left to right, you have to go left to right. Otherwise, you don't know when it starts to climb. You can tell when it starts to climb based on the group. But if we read it left to right, 3, 2, 1, that's a pattern.
Then 2 again,
No, not 2 again, because there's no oxate. We skip that, and then we go to fluorate. What would fluorate be? FO3. It doesn't go back up. It bottoms out at minus. Chlorate, ClO3 minus. It's a more complex pattern. It's not a simple pattern, but it's a pattern nonetheless that you can memorize. Just like, you know, the kingdom of the, you could memorize. It's just another pattern. It's not too difficult to memorize. Or you could, the other way, this is how I memorized. I didn't memorize it based on pattern. Do you know how I memorized it? I memorized it based on flashcards. So the first time I took my nomenclature test using flashcards, I started to hesitate when it came to the charge and the numbers. I couldn't remember, like for example, acetate, you know. So was it -2 or -1? What was it? And so I hesitated. Then I thought, okay, flashcards don't work for me. And then I wrote it down. I think I wrote acetate down like maybe between 100 and 500 times or something like that. And then it was just like, it's like, for me, riding a bicycle, I don't have to think too much. Well, I have to think about hitting something or getting hit, but I don't have to think about, you know, how to pedal and this kind of stuff. How to pedal is kind of automatic, you know? And it's like that. How much brain power do you have to use to pedal? And so the same thing, how much brain power do I have to use to write acetate? Nothing, because I've done it like 500 times. It uses 0 brain power. It was like muscle memory. And so this is the same thing. I mean, you have different ways you can memorize. You don't have to do this. If this doesn't make any sense, then don't do it this way. Do it a way that makes sense to you. That's what I had to do. I remember taking, did I tell you about the biochemistry class I took at UCLA? The biochemistry instructor gave a 25-page packet. I'd like to find it. You know, it's typewritten. Back in those days, it's typewriter was quite common. So it's typewritten, 25-page, how to study. And so I followed that. I tried it. It didn't. Some things were good. Other things just didn't work for me. So this is part of learning to learn. That's it. You got to find something that works for you. So, but I listened to all advice. Every suggestion I tried because it might work. I don't know. Well, let me give you an alternate way of solving these. This is two unknown. So this is the third method of problem solving that I was talking about earlier. One, we use conversion factors, which is the most common. Two is algebraic equations sometimes. Do that. Three, did I talk about three? Yeah, I did. Multiple equations and unknowns. In other words, system of equations, people call this. So we could do this really quick. This is a simple system of equations. So at what temperature does degrees Fahrenheit equals degrees C? So we want X degrees Fahrenheit to equal Y degrees C. So what are the equations? Well, one equation is X equals Y, and then another equation is, let's go, X is equal to 9/5 degrees C plus 32 degrees. So if we have two equations, like this, I'm going to just keep it simple. Like these two equations here, then we should be able to do it. But X is degrees Fahrenheit. That's going to equal, the degrees C is Y. So we change this to Y here. And so I'm going to do a little substitution here for this. There are different ways to substitute it. X is equal to Y, so Y is equal to 9/5 Y plus 32. And then solve this for Y. So I'm going to, what should I do? Subtract Y from both sides and subtract 32 from both sides. So I'm going to do 5/5. So this is going to give me 4/5 Y is equal to minus 32. Y is equal to, I didn't bring my calculator today. I use my phone. So 32 minus 32 times 5 divided by 4. Okay, it's minus 40. So that means the temperature, okay, let's just test this. Now Y is, what did I call Y? Degrees Celsius? So this is my degrees Celsius. So if Y is equal to minus 40 degrees, then what is X? Well, X is my degrees Fahrenheit, and my degrees Fahrenheit is going to be 9/5 times minus 40 degrees plus 32. And let's see if I get minus 40. And so minus 40 times 9 divided by 5 plus 32. And it comes out to minus 40 degrees C. So this works. So this is an example. At minus 40 degrees, the two thermometers are going to read exactly the same temperature. Does that make sense? Yeah. So an example of a two unknown problem. Did I assign this as homework? I think mastering Chem, it wasn't one of the options. I like this particular problem. And so that's another reason I hadn't adopted Mastering Chem for a long time, and I thought the price went down enough, but sorry. How much did the final price of Mastering Chem come out to? About 30? Okay. Was it 30 pounds? Yeah, I try not to make the class too expensive, so but it came out more expensive than I thought. And so this is why I don't like surprises. I like to try to keep the surprises on test to a minimum, and so this is why I like to look at all the questions on the test, because that was just one, that was like part A. There's a part B and part C to that particular question. Let's go back to, this is from chapter 1. I think that was It wasn't. So Fahrenheit and Celsius thermometer are immersed in the same medium. So they're recording the same thing. At what Celsius temperature will the numerical reading of the Fahrenheit thermometer be 49 degrees less? Okay, so we want the Celsius to be here and the Fahrenheit to be 49 degrees, and they're both stuck in the same liquid, let's say, or whatever, whatever you're measuring. Or double that. So we want the Fahrenheit to be double the Celsius when they're reading the same object. Or 1/8 that, or 300 degrees more than that. And so on the exam, I don't want to be surprised. So if I get hit by a question like this, I want to at least be somewhat prepared. So I just threw in another variation of this question. And so that would be part E. Part E would be the same temperature. Is there a temperature where the Celsius and the Fahrenheit would be recording the same numerical value? And the answer is yes. What is that temperature? Minus 40. And so this is one of the reasons. I wouldn't spend a lot of time on this. I would read the question and then look in the solutions manual what the answer is. Right? And so that's what I do. Now, some of these aren't going to be very worthwhile. When you look at some of these questions, okay, using tools that you used in Chapter 3. So the only reason it's an advanced problem is because they're making you do something that you did earlier and making some kind of composite question. All right, so that's one method. So if I wanted it 39 degrees less, then y is equal to x minus 39, and then just substitute, So, or if I wanted 1/8, then y is equal to 1/8 times x, and then substitute. And so it's not that difficult. And so this one I would do algebraically. But some of these problems I call the two equation problem. So for example, in Chapter 2 you had sodium chloride and magnesium chloride. This is the two equation problem. And so maybe I should do this one. I saw a lot of people did this one. Did it make sense how they did it? So actually, let me do that one. And then in Chapter 3, Chapter 3 is like the problem I just put on the test. I think the aluminum magnesium alloy or the methane ethane. These are all two unknown. Because what we want to know the percent. What is the percent aluminum? What is the percent magnesium in this mixture? Percent ethanol. Or that's not ethanol. What is that? 1 carbon alcohol. This is methyl alcohol. This one's ethanol here. Methane ethane. Okay. So all these are similar, and there's more. I think and they're all kind of the same thing. This is another reason I look at a lot of problems. So I see, okay, this is the same kind of problems. I use the same problem-solving method. And the problem-solving method that I use is different than the book. You could do it any way you want. You could do substitution. Solve for one variable, substitute it, the equation. That works. But I'm going to show you an alternate method for these particular ones that I think is a bit easier. At least for me. It only works for two variables. And so I'll do the Chapter 2 one since maybe more people have seen it. Maybe. What was it, 101? No. Maybe it wasn't an advanced problem. just get it from mastering rather than the book.
Professor,
Mm-hmm.
it's chapter 3.
Oh, is it chapter 3? Okay, that's fine. Thanks. Do you know what number from the homework?
101.
101? Okay. Yeah, there it is. This is a tutorial for number 39. All right, so we have some kind of mixture here, and this mixture contains magnesium chloride and sodium chloride in the mixture. The problem is this is table salt, and so there's a little bit of magnesium chloride in there. And magnesium chloride is used to prevent caking of the salt. Caking of the salt is like what you experience probably with the oxalic acid, where it cakes. It's hard to get it to break off the crystals, to separate, because the crystals are kind of stuck together. And so that's what happens here. Magnesium chloride prevents that. And so they add. The question is how much magnesium chloride? And so the unknown, the first unknown is we have this. We want to solve for how much magnesium chloride, so I'll call that Y percent. Okay, let's just say let Y equal the percent magnesium chloride. And then we're going to let X equal the percent sodium chloride. And so what we could do is we could do two equations. The equations I'd probably use are like something like this. X plus Y is equal to 100%. So that would be one equation. And then all we have to do is think of an equation 2. And then we could do the solve for one variable, substitute, you know, etc. But I'm going to show you the graphical method. And now the percent chloride is going to vary depending on how much magnesium chloride we have. So it varies. So let's say this were 100% sodium chloride. Let's say there was no magnesium chloride in here. So I'll show you the graphical method here. One, you assume it's 100% 1. So let's go ahead and we're going to assume it's 100% sodium chloride. If it's 100% sodium chloride, then that means all 0.5200 grams is pure sodium chloride. And so that means I'll have 0.5200 grams of pure sodium chloride. And then I need to get the percent sodium chloride from this. And so, percent chloride. The percent chloride is going to equal the grams of chloride over the total grams times 100%. So the grams of chloride we're just going to get from stoichiometry. So if we have 0.5200 grams of sodium chloride, how many grams of chloride do we have? And so what I'm going to do is I'm just going to use a little bit of stoichiometry to figure it out. And so I need the molar mass of sodium chloride. Sodium is 2299 or 2300. So let's take a look. I'm going to use 2300 because I'm only going to go 2 decimal places. Chlorine is 35.45. Chlorine is one I have memorized, but sodium I don't. So this is going to be 45, 8, 58, 95. So we have 58.95 grams per mole. And the grams cancels. That gives me moles of sodium chloride. And then I know the formula is a mole ratio. So I have 1 mole of chloride ions for every 1 mole of sodium chloride. Now, what we do here is we don't factor in the mass of the electron because the mass of the electron is kind of small. So if you take chlorine, which is 35.45, and add the electron, it does impact the mass, but we don't usually include that. Probably we should, but we don't. And so this is 35.45 grams per mole of chlorine. Should be chloride, but we're just going to use the molar mass of chlorine. And so this gives me grams of chlorine or chloride per 5,200 total grams times 100%. So if this were pure sodium chloride, we'll go 52 divided by 58.95 times 35.45. So I have 0.312. Out of that 0.5200, 0.3127 grams of it is chlorine or chloride divided by the total mass, 0.52 times 100. And so it gives me 60.135% chlorine. I'm going to add more sig figs than I'm allowed here. I'm allowed 4, but I'll write 5. All right, this is the hard way of solving for percent. All I'm going to do, the next one I'm going to do is the easy way. So assume 100% magnesium chloride. If it's 100% magnesium chloride, then I'm going to do the fast way. And this is why you want to be exposed to a lot of different ways of solving problems, because if you're exposed to a lot of different ways of solving problems, you have a lot of paths. It's like if you know the city well, then you might know the quickest way to get from point A to point B, whereas somebody who's new, they're just going to be following maybe Google Maps or something like that. It might not be the fastest way. And so the fast way of doing this is the percent chlorine is going to equal the grams of chlorine. Well, I have 2 chlorines, and 2 chlorines is 35.45 over the total. And so what is magnesium? Magnesium is 24 point, I can't even read that. 24.31. I'm going to round it. Although I don't know if that 5. I don't want to do a cascading round, so let me just look up the molar mass of magnesium. They only have 3 decimal places. All right, I'm just going to round it up. 24.31. So this is 24.31 plus 2 chlorines, which is going to be 70.90. Gives me 1, 2, 5, 14, 100, 104.21. So magnesium chloride total weighs 104.21. I'm going to assume I have 1 mole of magnesium chloride. If I have 1 mole of magnesium chloride, then I have 104.21 grams of magnesium chloride. I'm going to write the units in here, even though it kind of cancels. And this many grams of chlorine or chloride times 100%. Whether you do it this way or the long way, you're going to get the same answer. So I'm going to get 70.9 divided by 104. .21 times 100. 68. one has more chlorine? Sodium chloride, as far as percent goes, percent by mass. This is percent by mass. Sodium chloride only has 60% chlorine, whereas magnesium chloride has 68% chlorine. And so magnesium chloride has more chlorine by mass. Now, could this mixture be pure sodium chloride? This mixture has 61.1% chlorine. Could this mixture be pure sodium chloride? No. In order to be pure sodium chloride, it would have had to have 60.1, not 61.1. Could this mixture be pure magnesium chloride? This mixture can't be pure magnesium chloride because in order to be pure magnesium chloride, it would be at 68%. So what that means is this, you know, it's between 60% and 68%. You know. Let's say it were 64%. If this were 64%, then I'd say it's a 50-50 mix. It's halfway between 60 and 68. Does that make sense? It would be 50-50 mix. And so what we do is we look at which one has the higher. Which one has the higher percent chlorine is going to be magnesium chloride. And so what I do, this is why I call it the graphical method. I call it the graphical method is because I'm just going to graph it. I'm going to start at 60.1. 60.135%. Actually, I need this on the y-axis, sorry. I'm going to move this. Okay, so this is there, it's supposed to be there. And then it's going to go all the way up to 68.035%. Chlorine here. And then on the x-axis, I'm going to write this. I'm going to write 0% on 100%. And I'm going to pick the bigger one, magnesium chloride. So if we're at 100% magnesium chloride, what is our percent chlorine or chloride? 68.035. And so my first data point is going to go here. If we're at 0% magnesium chloride, that means we're at 100% sodium chloride. And if we're at 100% magnesium chloride, that means we're at 0% sodium chloride. And so we're at 0% magnesium chloride, 100% sodium chloride. What's the percent chlorine? The percent chlorine is 60.135. So we're here. So what we know is this is going to be linear. You know, there's no squared terms in the stoichiometry or cube terms. It's just linear. And so there are two ways we can do this. We can just go to 61%. And this is a poor graph, but if I'm at 61%, it's about here. So guesstimate for me how much magnesium chloride I have. I'd say maybe about 10%, 5 to 10%. What would you say? Yeah, something like 5 to 10%, maybe less. My graph is not good. But better than doing the graph, we just do the equation. What's the equation for a straight line? Y equals mx plus b. And so this is pretty fast. What is y? Y is the percent chlorine. So the percent chlorine is equal to m, the slope. The slope is delta y, so 68.035 minus 60.135. and the units here would be percent chlorine, over delta X, 100 minus 0, percent magnesium chloride, times X. X is what? X percent magnesium chloride. Is that correct? Plus the intercept. What's the intercept here? 60.135% chlorine. Chloride. This is percent chloride. So we're just going to solve for X. So that's my equation for the straight line. And then I'll solve for X by just plugging in my percent. This percent was 61.1. Did they only give 3 sig figs in the problem? 61.10. That's my Y, is equal to my slope. So let me just calculate the slope here, which is going to be 68.035 minus 60.135 divided by, well, divided by 100, yeah. 0.079. Now I have 5 sig figs. So I'm just going to put a 0.079 thousand. And this is going to be, units are going to be percent chlorine divided by percent magnesium chloride. And then we're solving for X percent magnesium chloride. And then this is going to be plus the intercept, which was 60.135% chlorine. So I'm going to subtract 60.135 from both sides, I think. That'll be maybe the easiest. So I'm going to go 61.1 minus 60.135. Actually, wait a minute. I think I miswrote something. Let me take a look. 60.135. Yeah, well, let's try it. 61.1 minus 60.135 equals 0.965. So 0.965% chlorine is equal to 0.079 thousand. I'm just keeping track of sig figs here. I should, this pen is a little bit too thick. Units here would be percent chlorine over percent magnesium chloride times X percent magnesium chloride. Okay, now I'm going to divide both sides by this, the slope. And so 0.965 divided by 0.079 is equal to this. So that gives me X percent magnesium chloride is equal to 12.215%. And so to 4 sig figs, it would be 12.22% magnesium chloride. So we I guess I kind of guessed. I said 5 to 10%. It was more. It was like 12% off the graph. Just my graphing was bad.
When you do the denominator out of the whole for scroll up a little bit. Up more. Yeah, way up. Yeah, here. Down a little bit. Okay. So when you do the denominator, you get 104.21, but shouldn't it be like around 70 for the 2 carbon, because the mass of carbon is around like 35, and when you double 79.
You accidentally wrote carbon.
Oh,
Sorry.
Oh, that's, yeah, my bad. No, I totally just fudged that.
Actually, I screwed this up. It's supposed to be 70.90.
Oh, yeah, yeah, yeah. No, I did.
I screwed that up.
Yeah, science is being like,
Yeah, let me redo this calculation here. This is supposed to be 70.90. This is why I try to avoid doing calculations in my head. Do it on the calculator. Yeah, sometimes I just screw it up. Yeah, 2 times 35 is 70. 2 times 45 is 90. So 70, 90. So it should have been 70, 90. How does that change the mass? So we'd go back and we'd just add this. What is it? It's going to be 9521. Is that correct? 9521 grams of magnesium chloride. Yes. All right. Yeah. Sorry about. We'll just fix that right now. 9521. And so let me redo this calculation. So it's going to be 70.9 divided by 95.21 times 100. 74.46. It's 466. Don't round it. Don't round it. You got 74.4669, correct? We don't want to do a cascading round because I'm going to carry an extra digit here. Yeah, I was thinking 10% magnesium chloride and table salt was way too high, so that's why I was leaning towards 5, and I was hoping my graph was way off because they don't put that much anti-caking. It's when you buy table salt, it's mostly sodium chloride, and so I was thinking this graph, I was trying to tweak it down. You know, maybe 5%, but even 5% was kind of high. But 12%, you know, 12% magnesium chloride in table salt is a lot, and probably they shouldn't call it. They should call it something else, you know, sea salt or something. Sea salt, you can have whatever in there. But unfortunately, I screwed that up, and so I'm going to just redo this. If you make a error like I made here, and unfortunately, I'm just wasting time, but in the lab, don't tear out your lab manual pages. We never tear out pages in our lab manual. So if I make a huge error that takes up half the page like this, we'll just exit out and leave it. This is in your lab manual. You could do whatever you want in your lecture notebook. It doesn't matter to me. Okay, then why don't you set it up for me? $6.73. Did anybody else get that?
what was the number?
6.73.
I got something similar to.
What did you get?
I got 6.74.
6.74, 6.73. So this is kind of the peer review process when we're checking. These I would treat the same. It's just some rounding issues. So Mastering Chem would treat those as equivalent answers, probably. Although they might want you to have one more sig fig in there. And give me 4 sig figs in your answer. All right, so what you're going to do, for those of you who are, you're just going to, this thing I X'd out here, you're just going to kind of copy this, but just change this number here, and that's going to force you to recalculate the slope. The y-intercept's going to be the same. Okay. And then you'll just get a new y equals mx plus b. All right, so that's from chapter 2. This is from chapter 3. That was from chapter 3. This is from chapter 4. A 0.27 gram sample of aluminum magnesium alloy reacts with an excess of hydrochloric acid to produce 0.0249 grams of hydrogen. What is the percent magnesium in the alloy? So this is the same type of situation. Both of these react with hydrochloric acid, but what happens is they produce different amounts of hydrogen. You know, so for every gram of, let's say on a per gram basis, what produces more hydrogen? Aluminum or magnesium? So this is a very common multiple choice question on like standardized exams. Which one produces more hydrogen per gram, aluminum or magnesium? And they say without doing any calculation. Without doing any calculation, which one produces more? You'd have the periodic table. So how much does 2 moles of aluminum weigh? Well, how much does 1 mole of aluminum weigh? 26.98. So let's call it 27 grams. So 27 grams of aluminum. And 3 moles of hydrogen weighs how much? So 3 times 2 is 6 grams, right? And so 27 grams of aluminum produces 6 grams of hydrogen. How much does 1 mole of magnesium weigh? 24. We'll just call it 24 because this is supposed to be done without calculation. This is supposed to be done in your head. And how many grams of hydrogen does that produce? 2 grams. So which one produces more per gram? So in order to produce 6 grams of hydrogen, we'd have to have triple the amount of magnesium. Triple the amount of magnesium would be like 72 grams. And so 72 grams would produce 6 grams of hydrogen, whereas 27 grams of aluminum would produce 6 grams of hydrogen. You see? And so this is very common. With multiple choice, you have a different strategy. This is, you know, I told you at UCLA I only had 1 class with multiple choice exams. Did I tell you that? Maybe I didn't. I was, you know, being a physical science major, I tried to avoid, I had to take biochemistry, of course. That's a major's requirement. But I tried to avoid the biology classes because the biology classes at UCLA are pretty tough. You know, so especially the main biology courses there. And biology's always been tough for me because there's always a lot of memorization. It was always hard, including biochemistry. You know, I had to memorize the tricarboxylic acid cycle and the Krebs cycle, basically, and other stuff. It was a lot of memorization. And so I had to use all the memorization techniques. You know, I wrote down, I don't know how many times I wrote down the Krebs cycle. A lot of times. But anyway. So I was looking for the easiest life science course to take because I had to take a life science course. So everybody said, oh, take paleontology. Paleontology is the easiest life science course. So I took it. It was all multiple choice. And the multiple choice questions weren't tricky. Multiple choice questions were straightforward. And so that was it. And then I had to take the GRE. Have you heard of that test? This is a graduate record exam, you know, after I graduated or before I graduated. It's to get into graduate school. I took the GRE and then I took the chemistry subject test. Those are all multiple choice, 100%. And
You have to take that exam to skip getting a master's, or is it something that you have to do?
you have to do. Even if you were to get a master's, I think you have to take it. So the GRE, everybody, it doesn't matter what your major is. So the math on the GRE is algebra. It doesn't go beyond algebra. So I thought, algebra, I'm not going to study for that. I didn't. And then I did worse. I did very poorly on the algebra. I got like 78%, something like that. 78% is awful for science. So when I went to interview at graduate schools, everybody asked me, why did you do so bad on the math? And I thought the same, why did I do so bad on the math? And it's because then after that, actually immediately after that, after I saw my score, I did, you know, on everything else, including, I couldn't believe it because I thought I was going to do the worst on verbal. But on the GRE, I did the best on verbal, which shocked me. But I also prepared for that. But what I did was I bought an old exam. They have these old exams. So I bought an old GR math exam book, and I went through the questions, and I realized why. You know, I just wasn't used to answering multiple choice, and some of them were very tricky. Very tricky. And so there's a certain like skill and certain techniques that you use to go through multiple choice questions quickly, which I didn't bother doing before those tests. You know, on the Chem was no problem. That's why they overlooked the math. The Chem was good. But anyway, this they're like this, you know, like how much time would you waste? If you've never done something like this, how much time would you waste? Which one gives you the highest hydrogen per gram content? I'd probably waste like 5 minutes. You know, that was like me, because I haven't, like, wow, I've never dealt with that kind of question, so I'd overthink it, you know? It wouldn't be quick. So, which one gives more hydrogen per gram? Aluminum. And so it depends on the composition of the mixture. If this were pure aluminum, it'd give a lot of hydrogen. If there were pure magnesium, it'd give a lot less hydrogen. But we got this, and so what we can do is we can identify the composition of the mixture based on how much hydrogen is produced, because different compositions will produce different amounts of hydrogen. And so this is what I call the two unknown problem, just like the last one. And so what do? There are two ways to solve this. One, you can generate two equations and then do substitution. I don't like that because it's too much algebra. Even though you might think graphing, what a pain, but graphing is so much easier because it's just y equals mx plus b. And so how would I do this? Well, I'd use the same technique. The first thing I would do is I would assume it's 100% magnesium, let's say. It doesn't matter which one you start off with. I'm just starting off with a smaller one. 100% magnesium. So all 0.275 grams of this is magnesium. So 0.275 grams of magnesium. And then we're going to convert that to moles of magnesium. The molar mass of magnesium is 24.31 grams of magnesium per mole of magnesium. And then we're going to convert that to moles of hydrogen. 3 moles of hydrogen per 2 moles of aluminum. And then we're going to convert that to grams of hydrogen. 2.016 grams of hydrogen, H2 per mole of H2. And so let's see how many grams of hydrogen magnesium produces. You know, 0.275. Uh-huh.
I have a question. And so the 275, it's talking about the alloy with aluminum. And
Yes.
nickel. So how come you're treating it just with the magnesium?
This is it. If you go to, let's say, a forest, right? And the forest is a mixture of trees. But you're studying tree height. And so what do you want to do? When you're studying tree height, do you want to study all the middle trees? No, what I'd look for is I'd look for the shortest tree and the tallest tree. And then I'd say every other tree is between the shortest tree and the tallest tree. That's what I do. So every composition of alloy is between pure magnesium and pure aluminum. So all I'm doing is I'm looking for the smallest and I'm looking for the biggest, and then everything else is in between. That's what I'm doing here. And so this is going to be the smallest. The smallest amount of hydrogen is going to be 0.034 208. Actually, I have way too many digits, but this is going to be grams of hydrogen. And so the first thing I asked is, can this alloy be pure magnesium? That's a trick question. They might tell you it's a mixture, but it turns out to be pure. We can figure out if they're lying or if they're telling the truth. You know, they're telling me it's an alloy, but no, it's pure, because if the amount of hydrogen produced, let's say this alloy produced 0.0342 grams of hydrogen, it's not. That should be like 100% or close to 100% magnesium, or yeah, magnesium. Does that make sense? All right, then actually this is going to be the biggest tree. The smallest tree is going to be if it's 100% aluminum. Or is that the smallest? No, this is the smallest, sorry. The biggest is going to be if it's 100% aluminum. I don't even know. You don't have to know what's the biggest and the smallest. You just do the calculation. The calculation tells you. You don't have to overthink this. And so if we assume 100% aluminum, what do? We're going to assume all 0.275 grams is what? Yeah, we're going to assume all 0.275 grams is aluminum. It's pure aluminum. So what we're saying is, oh, they're lying. It's not an alloy. It's just a pure metal. If it's pure metal, then it's going to go, well, I shouldn't say they're lying. It's just they have it wrong. But we can figure it out, you know, if they have it wrong or if they have it right, if it's an alloy or not an alloy. We'd probably do more analysis, though. What am I doing? Aluminum, what's the molar mass of aluminum? Yeah, we go there, 26.98. Is that correct? 26.98 grams of aluminum per mole. And then we're going to go from moles of aluminum to moles of hydrogen. What's the mole ratio from the equation? It's going to be 3 to 2. So 3 moles of hydrogen for every 2 moles of aluminum. And then we're going to go to grams of hydrogen. And so this is going to be 2.016 grams of hydrogen per mole of hydrogen. And so let's see what we get here. And so this is going to be 0.275 divided by 26.98 times 3 divided by 2 times 2.016. 0.0308 2 grams of hydrogen. I must have made a mistake. Oh, the mole ratio's off for magnesium? Yeah, I looked at the wrong equation. And so this is wrong, sorry. The correct mole ratio is 1 to 1. I was looking at the wrong equation. It was rushed. But what we should do is go back through. I could tell this is a mistake because this should be in between the biggest and the smallest, right? And it wasn't coming in between the biggest and the smallest, so I knew I must have made a mistake. And so let me recalculate the magnesium. It's 0.275 divided by 24.31 times 2.016. 0.0228. So if I'm 0.5, let's go with that, grams hydrogen. So basically, the smallest hydrogen would be 0.0228. The biggest hydrogen would be 0.0308. And so how much hydrogen do we have? 0.0249, which means it's closer to the smaller one or closer to the bigger one, or halfway between. It looks like it's closer to the smaller one, so this mixture should have more magnesium than aluminum. Right? It's closer to magnesium, therefore. And so you're studying the trees. Oh, this tree in the middle, this one's closer to this big one here rather than the small one, or it's closer to the small one rather than the big one. So this is linear. We assume it's linear. We don't have to assume. There's no squared terms or anything in the stoichiometry. So what we do is on the y, we're going to write down grams of hydrogen on the y. On the x, I'm going to pick the bigger one. What's the bigger percentage? Or the bigger hydrogen in this case? The bigger one is going to be aluminum. And so on the y, what are my units? Percent aluminum. Good. And so we're going to go from 0% aluminum to 100% aluminum. If it's 0% aluminum, how much hydrogen do I generate? Well, if it's 0% aluminum, it's just pure magnesium, and I'm going to get 0.0228. And so Y1 is 0.0228 grams of hydrogen. And if it's 100% aluminum, I'm going to get 0.0308. So Y2 is going to be 0.0308 grams. And then I'm going to have two data points, here and here at the origin, right there. And then I'm going to assume that this is linear, which it's going to be linear. Oops. And this is y equals mx plus b. And I'm going to make sure the line intersects the data points there. Y is grams of hydrogen. So we're going to have y grams of hydrogen is equal to the slope. The slope is going to be y2 minus y1, 0.0308 minus 0.0228. That's going to be grams of hydrogen over 100 minus 0 is just 100. And so the units here will be grams of hydrogen over percent aluminum. And then the intercept is 0.0228 grams of hydrogen. Oops, I forgot my x. The x here is percent aluminum. Here. And then solve for percent aluminum. And so x percent aluminum is equal to the grams of hydrogen, which was 0.249, 0.0249. Minus the intercept, 0.0228, divided by the slope. Just calculate the slope out. I'm going to skip a step. 0.0308 minus 0.0228 gives me 0.008 divided by 100 gives me quadruple 08. And so divided by quadruple 08. And then I'm allowed 3 sig figs in the slope, so I'll call it 800. And the units for the slope are going to be in grams of hydrogen, which will cancel, divided by percent aluminum, which will be inverted and flipped. And so we'll get the percent aluminum. And so I'm going to invert this and then multiply by the difference. Or maybe I'll just here on my calculator. Keep getting these. Let's invert that times 0.0249 minus 0.0228. Oops, no. Sorry. Did I get that right? Yeah. 26.25% aluminum. And then I'll double check my answer. If it's 26.25, then the rest must be magnesium. So it's going to be, 100% minus 26.25% gives me the percent magnesium, which is 73.75% magnesium. And so this alloy is 26.25% aluminum, 73.75% magnesium. That'd be the composition. And then, of course, I double check to make sure that I did everything correctly. So. All right, so this is an alternate method for solving the two unknown equations. You could use whatever. You could use the algebraic method that they do in the book, or you could use the graphical method that I do here. All right, the other problem I was working on was the percentages. And so let me finish that problem here that we started the other day. And so it was dealing with all the percentages that we had. And that was from chapter 4. percent compositions. So now we have a mixture problem, but we solve this in a different way. Chalkboard chalk is made from calcium carbonate and calcium sulfate. So we have a mixture, so this might be one of those two unknown. We might do the graphical method. Let's see about this one. With minor impurities such as SiO2. Well, this is actually a more complex mixture because now there are 3 components. Sometimes we could make a 3-component, 4-component into a simpler one. So it's calcium carbonate plus other junk in there. And the other junk in there doesn't react. This is one of those because the calcium sulfate is fairly unreactive, and the silicon dioxide, or SiO2, is fairly unreactive as well. The calcium carbonate reacts. And so that's what they tell us here. Only the calcium carbonate reacts with dilute hydrochloric acid. And so that makes it a lot easier. In the previous problem, both react. Aluminum and magnesium reacted with hydrochloric acid. In this problem's worlds easier because only one thing reacts in this mixture, and that one thing is calcium carbonate. What is the mass percent of calcium carbonate? So they want the percent composition, but this is easier because they aren't asking us for the percent composition calcium carbonate, percent calcium concentrate, or percent composition calcium sulfate, and the percent composition silicon dioxide. They're only wanting one component. So what we can do is we can treat this as kind of a 2-component, calcium carbonate plus other junk. And then it's much easier because the other stuff does not react. So this is just basically, I don't know why they put this in advance. This would be like a Chem 4 style question. But this is an advanced problem here. So what is the mass percent calcium carbonate in a piece of chalk if 3.28 gram sample yields 0.981 grams of CO2? So this is a mixture, but we know that all the CO2 comes from calcium carbonate. And so even though it's a mixture, it's very simple, so we could just treat this as a plain problem. And so we could figure out how much calcium carbonate was in our original mixture just by stoichiometry. So 0.981 grams of CO2, and then carbon is 1201, oxygen's 2 oxygens 32, so it's 4401. 4401 grams of CO2 per mole of CO2. And then what's the mole ratio? It's a 1-to-1 mole ratio. So 1 mole of calcium carbonate per 1 mole of calcium carbonate per 1 mole of CO2. And then grams of calcium carbonate. So calcium is 40.08. Carbon is 1201. 3 oxygens is 4800. And so that gives us 90100.08. Thanks. 100 point.
You said 0.08.
0.09, sorry, 0.09 grams of calcium carbonate per mole. But that's not what they want. What they want is a percent calcium carbonate. So I could do this as 2 separate problems, or I could do this as 1 combined problem. If I do it as 2 separate problems, I'll do it like this. I'll do percent calcium carbonate is equal to the grams of calcium carbonate over the grams of mix times 100%. And so the grams of calcium carbonate is we start off with the grams of CO2 and then convert that to moles, and then convert that to moles of calcium carbonate, and then convert that to grams of calcium carbonate, just using stoichiometry. So that's what I set up below. Divided by the grams of sample, or the mix, is 3.28 grams of mixture times 100%. So this is total. So I could set up as one problem, or I could set it up as two separate problems. So I transfer all this into the numerator, and the other option is just to calculate the grams here and then plug it in to the equation. Percent calcium carbonate is equal to the grams of calcium carbonate, which is here. And so I'll plug that in here. That's going to be grams of calcium carbonate over the grams of mixture, which was 3.28 grams times 100%. And so this is, I think they had harder problems in Chem 4, but that's one of the mixture problems here. All right, I'll stop here. Well, anyway, good luck with the test. I have office half hour now, but it's going to be in Chem 108, so if you have some additional questions, we can go through that. I'm sorry?
What should I tell Dr. Mosquito? Do you remember, like, I was supposed to tell him?
Doctor who?
Mosquito.
Mascara?
Like president of
President of